Good morning, everyone. First of all, thank you very much for giving me the opportunity to present at this workshop, and thank you very much for organizing this event that will open the way for future editions, hopefully. So for those of you who don't know me, my name is Karakas, as just Stefan said. And I graduated from the Tectonic Lab from IPG. I did my PhD with Rolando Armijo and Robin Lacassin back when Robin was leading the group on the propagation of the North Anatolian Fault to the Marmara Sea 5 million years ago. And after that, I joined Paul's team at the Earth Observatory of Singapore, where we worked on the main frontal thrust in Nepal and in Northeast India. And today I'm here on behalf of SLB, and I will be presenting to you on behalf of my former SLB colleagues and my present SLB colleagues some projects they have worked on previously. And those projects are around this methodology developed and transferred to, I would say, all of us, multi-scale pluridisciplinary data integration. From natural hazard assessment to energy exploration. And we have seen in the past couple of days that this can be applied to many fields in earth sciences. Thanks to Paul and all of you. So I will be walking you through 4 use cases or projects that were initiated from discussions with Paul that led to ideas that led to proof of concept within SLB and the research team in Stavanger, Norway. Those proof of concept then gained visibility in Norway and internationally and turned into projects, client projects and collaboration projects with universities. And after those 4 examples, I will move into a new generation or new digital technology integration for subsurface interpretation, and then conclude with some ongoing collaboration and future opportunities maybe. But first, a few words on SLB, formerly known as Schlumberger. SLB is a technology and innovation service company that is present in over 100 countries around the world. It's a very international environment with over 140 nationalities and has 12 development and technology centers around the world where present day and future products are engineered and developed to be applied in fields from exploration to production. And in addition to that, more recently, 7 innovation factories were established, I would say 3 years ago, around the world again. And I work at one of them in Oslo. Here. And in these innovation factories, we also develop new technologies, but with a more R&D approach. And we work on a project basis with clients, trying to tailor new solutions and address the challenges they have. And I will be showing you a few past and ongoing collaboration towards the end as well. So, one of the challenges in subsurface interpretation is that the interpretation relies on different types of measurements coming from seismic data and down to smaller scale data set, well logs and even thin sections. And the challenge is that there is a resolution gap between these different scales and challenges in tying the information extracted from kilometric to 10 kilometer, for example, scale of data sets down to metric, centimetric, and even smaller scales. So in order to overcome this challenge, one way to address this is to find an analog. And here, back then, the solution proposed was to use outcrops as analogs for filling this gap, resolution gap, and start the application of this multi-scale data integration methodology. But of course, as we have seen in the past couple of days, there are existing solutions to do that, from data acquisition using different techniques such as the LiDAR and the UAV. You have different softwares that help you build a 3D digital model. interpret that, and then feed into a knowledge database to be used for further interpretation and understanding of the evolution of the landscape you're looking at. But yes, actually the challenge here is that you have to use several different toolboxes for each step and several softwares to be able to proceed to the next step. And sometimes even when you build your knowledge database, the systematic use of this knowledge is not necessarily done. So the team in Stavanger came up with an idea inspired by the discussions with Paul back then to use actually a software that you probably all know, or most of you know, that is called Petrel, where you can, after acquiring all the data you need in the field, import the data set and start your journey, as we would say, in Petrel, to digitalize your model, use interpretation tools, and build your data lake to then use it as a geological expert system-based interpretation. And in addition to this proposition, the use of these automated tools that are developed by the SSR team. SSR stands for Schlumberger Stavanger Research, that does not exist anymore, but is within the innovation factories now. Tools that help the interpreter to interpret efficiently the data set and adapt it to this type of data set, surface data set, that is not so commonly used actually in oil and gas exploration purposes. So here is how the workflow would look like from Paul's vision, actually. We call it integrated workflow because it starts from the acquisition in the field, then the integration of the data into this Petrel platform. You start building your model, turning your objects into Petrel objects, so objects that are readable by the software. And then you start using the different tools that are prototypes or existing plugin in the software to interpret your landscape. And once you reach a point where you have a convincing interpretation, you can use this interpretation to build a model. So using another tool called the geological process modeling, that will allow you to understand the evolution of the depositional units in this area of interest, and use that model to build or generate a synthetic seismic. And this synthetic seismic data will be used as an analog for the next step, where you will interpret your subsurface. So where you don't have real access to the subsurface, you can use this data to fill in the gaps. Just to focus a little bit more on the proof of concept of this workflow, that is the first part, the upper part here. The data set that helped Marie Etchebest, who is present here today, to prove the concept comes from the collaboration of Paul with our Chinese colleagues and colleagues at IPG. So the Earth Observatory, CEA, and IPGP. Data collected during fieldwork along the Fuyun Fault in the Karashingar extensional basin in China. So the LiDAR data that was acquired there was used to prove the first part of this workflow, where the data set was transferred into Petrel, turned into readable objects, different textures, different formats. And then other plugins that are and were developed at that time in the research team were used to characterize the surface and start the interpretation. So you can generate several types of 3D geometrical attributes on your surface and start highlighting the structures, as you can see here, fault scarps. And you have tools to filter those scarps out and then run an analysis on the azimuth distribution and start your fault distribution analysis in that area. So this project gained a lot of visibility within Norway, and the team, I think this was in 2016 or 17, was approached by the Southeastern University of Norway and by a company called Aker BP. Because they wanted to test if this integrated workflow could be used on their data set to address the challenges they had. So their area of interest was in Svalbard, south of Svalbard, where they had the offshore data, but a hard time interpreting that data set. So what they wanted to try was to acquire surface data onshore and then apply the workflow I just presented to you and see how well they can model the geology in the subsurface. But in addition to that, they wanted to do that on the cloud because they projected that they will keep on having data, acquiring data onshore and offshore. So they wanted to have this workspace in the cloud where they could continuously add data, update their interpretation, and update their geological model. And in addition to that, they also wanted to make all this accessible to new employees that would come in and would like to be trained on this data set and do the whole workflow from acquisition to interpretation and to modeling, so that nothing is lost between generations. This was a very successful project back then in 2017-18. Another way of integrating data in this Petrel platform was tested, or as a complementary study was tested in this study, the 1950 Assam earthquake study. So just a little bit of background. Actually, Li Qingjiao has touched upon this a little bit 2 days ago. The terraces, the uplifted terraces along the main frontal thrust and a little bit, I think, around the Mishmi thrust as well. But just to come back a little bit into the context, so although the magnitude 8.7 1950 Assam earthquake endures as the largest continental earthquake ever recorded, its exact source and mechanism has been a subject of debate. And this paper discusses or proposes a joint analysis of the spatial distribution of reappraised aftershocks and landslides and add new field evidence. I'm sorry. And add new field evidence for its hitherto unknown surface rupture extent along the Mishmi Hills here in the eastern part and the Abor Hills in the northwest. And all the observations likely attested to minimum 200-kilometer long rupture, a surface rupture on both the Mishmi thrust and the main frontal thrust here in the northwest. So to complement the study, this morphotectonic analysis, the data set was integrated, the whole data set was integrated to Petrel to calculate planar surfaces. And planar surfaces that were fitting both 1950 surface fault traces in the main frontal thrust and the Mishmi thrust. So several scenarios were tested, and I will invite you to go and check this paper to have a flavor of the discussion there. Then the last example I wanted to talk to you about is the Ockness slope instability. As I was saying, this approach gained a lot of visibility within Norway, and the team was then approached by the NVE. NVE is the Norwegian Water Resources and Energy Directorate. And so they wanted to have a way to address this slope instability in Western Norway. So a little bit of background for this area in general. So rockfalls and rock slides are among the most serious natural hazards in Norway, mainly because of their tsunamigenic potential. The three most serious natural disasters in Norway in the 20th century were related to tsunamis triggered by massive rock slides into the fjords and the lakes and the surrounding lakes, causing 170 fatalities. So the Ockness site is located in western Norway, where steep valleys are within this extensive fjord systems. In these extensive fjord systems, prone to gravitational failures. So as you can see on this image, the potential rock slides in this region have been in strong focus since a while back, actually. And as stated here, preliminary results of tsunami modeling suggest an inundation height of up to 35 meters in Hillesilt for a rock slide volume of around 35 million cubic meter at this Oknes site. So in this context, NVE was looking for a software platform to integrate and analyze, present their data set in systematic way. So being able to use all this data set in this platform to build 3D static and dynamic geological models of the Oknes instability, and then to compute the volume of unstable rocks and evaluate the possibilities for risk reduction through draining. This was conducted as a pilot study, and if successful, they could be deployed in other sites in Norway. This was so NVE and SLB signed a multi-year collaboration agreement involving applied research and field test activities, where both parties actually benefited from a two-way transfer, knowledge transfer. And this brings us to this part on the new digital technology integration for subsurface interpretation, but for surface interpretation as well. It's valid for that as well. So SLB is very active in developing technologies using artificial intelligence. I think it's important to say that geologic characterization of the subsurface is important for the success of a wide range of applications, not only oil and gas, but it can also be applied in renewable energies and civil engineering. And so this work presents a deep learning assisted framework to interpret geological features in the subsurface from seismic data and well data. And specifically, the workflow integrates 3D convolutional neural networks trained to target specific geological objects such as salt, faults, and stratigraphic boundaries. So the networks can be trained in a very flexible way, so with an iterative process. So you can use a local training using calibrated well markers, discrete logs, add in this to the pipeline, train the network, deploy it on the seismic data, for example. If you're not satisfied, you can go back, add on some calibrated 3D seismic interpretation. So you interpret inlines and cross lines, add that into the training, train your model, and then test again. You can also use global training where you generate synthetic seismic data with faults and deploy it to predict fault network on your data set, and also use some properties, synthetic properties to train your machine to learn on recognizing these patterns in your data. To test this framework, we have used an open data set, the Groningen gas field, released in 2020. This is a very rich data set in terms of data, but also in terms of interpretation. So we had access to a 3D seismic cube with a large amount of wells and a large amount of digital wells, and also seismic interpretation and well tops plus a geological model. So we had the data, and we had also some information as a reference and as a ground truth to validate the tests we run with our deep learning framework. Yes, so just to give you an example on salt body delineation, how it works. So the training data here is composed of the top and base of the salt markers identified at each wells. And then the output of this, so you train by using these markers, and you deploy the train network on the whole data set, and what you obtain is this salt mask volume, plus the top and base salt as surfaces with their respective prediction uncertainty. So here the surfaces are also predicted. You can use the same approach for faults. We can discuss the details later if you wish, but just to give you a little focused view of the prediction against the interpretation. So in white, you have the fault interpretation provided in the data set, and in blue, the prediction using the network trained for this. What you can notify is that the two fault networks are consistent in terms of azimuth and their distribution, but there is a shift when it comes, so there is a difference in their exact location with a specific shift. And that is due to the way the training data is generated. And here it's easily explainable by the fact that the training library is actually defined as a discontinuity of the seismic signal. So as a result of such training, we ensure that there is a signal consistency of the predicted fault. So yeah. You can also add to your training additional constraints by generating seismic attributes that will highlight the structures you're targeting, and add this to dictate or force the network to recognize this type of patterns that you know are present in your data set. So you can control very well, step by step, the evolution of your prediction. And the end product, the output, is a volume of probabilities of the presence of sequence boundaries. So you will have a prediction of boundaries of units, a salt volume, and also a fault volume that you can then assess. This kind of approach can be applied on many areas. So as I was saying, subsurface, but also you can train networks on subsurface data and deploy on surface data, bathymetry, or even topography to predict different objects. Here we tested this on an open data set in the North Sea, which is an area considered for potential CO2 storage. And we were looking for a prediction or a detection of pock marks in the area, pock marks that are potential markers of fluid or gas leakage in the surface. So this was a quite successful test that needs, of course, more testing and improvement with additional data sets. This approach can also be applied on surface fault mapping. Using all the fault maps you have produced in the field, we can feed the network and predict on large distances, a large number of faults. So, yes, that brings me to the last slide of the presentation soon. But I just wanted to say that I hope that it's clear that all the work that we have done here was possible because of continuous collaboration with universities and being involved in ongoing research. And this is something we promote every day, and this is something we continue doing. Here is an example of this. So SLB joined GMG, Geomechanics and Mitigation of Geohazards Research Center, a couple of years ago. Maybe most of you have heard of this. This is a center that is in Caltech, that is directed by Jean-Philippe, and large expert teams. And I believe that the SLB team in Boston is very closely collaborating with GMG teams in addressing challenges with the focus on CCUS and maybe geothermal as well. We also like to be involved in fundamental research. This is an example from a small project we had with the University of Côte d'Azur. It's Frédéric Leclerc and her master student at that time, Sylvain Palagonia, where we tested automated tools to assist efficient seismic interpretation for hazard analysis. Here we benefited from this data set bathymetry. So, still trying to adapt the tools we are developing for subsurface on other types of data sets. And we continue also on working more locally. This is the North Continental Shelf 2030 Consortium, funded by the Norwegian Research Council of Norway, where we also contribute in training PhD students on interpretation tools, testing and developing further automated tools for efficient seismic interpretation. So promoting continuous two-way communication and two-way knowledge transfer is very important to continue innovating and developing new technologies for this energy transition time we are in. Thank you very much for your attention.